Here is the question that I asked at the end of the previous part of this lecture. And of course, the way you do this is the area under the graph, and that divides up into a rectangle and a triangle, and if you do that calculation carefully, you should come up with 20 joules. We can use our newfound ability to find work due to variable forces to find potential energy functions. And so, as an example, let's do that for spring potential energy. So we'll think about compressing a spring with a brick, a very familiar situation. The brick is going to be stationary both at the start and the end of the process, and the system is the spring alone. And so that means there's no change in the kinetic energy, and all that happens is that external work is done by the brick, and the system gains spring potential energy. And so that just says that the final spring potential energy is equal to the work done on the system, and that work done on the system is work by the brick on the spring. We want the work that the brick does on the spring as the spring is compressed, and we know the force function that describes the force exerted by the spring. That's Hooke's law. And so Newton's third law says that the force that the brick exerts on the spring is just positive k y minus y0. Now, before we go any further, it's a good idea to look at some signs of things. The way I have my axes set up, y0 is greater than y. And so y minus y0 is going to be negative, which means that F that the brick exerts on the spring, the y component, is also negative. But that's not telling us anything we didn't already know. That's just saying that this force points down. But the other thing to note is that the force displacement vector and the force doing the work point in the same direction. And so we know that the work that the brick does on the spring is going to be positive. So now we know the signs that everything should come out to. What we now can do is use our definition that we have, that our work that the brick does on the spring is going to be the integral from y0 to y of the force that the brick exerts on the spring as a function of y dy. So continuing to write out this integral and using our expression for the force, this is the integral of k y minus y0 with respect to y. And this is one of these integrals that you can evaluate without knowing any calculus, because remember, it's just the area under a curve. And so here is the graph of that force versus y. And at y0, we know that that force is 0, and it's linear. And here's y, and the area we want is right here. And in fact, this is one of these cases where if you know calculus, you might be more confused than the people who don't know calculus, because you'll be looking at this area and saying, wait a second, it's under the axis. Shouldn't it be negative? But we know this work is supposed to come out positive. Well, if you know calculus and you're confused by that, note that we're integrating from y0 to y, so we're actually integrating backwards, and that's why the sign is coming out in an unexpected way. However, if you don't know calculus, I hope you're looking at this and saying, well, it's a triangle, and I know how to get the area of a triangle. It's a half the base times the height. And so the base is right here, and it's just y0 minus y, where I've done it that way so it comes out positive. And the height is just here, and it is just the force evaluated at y. Well, that's k y minus y0. except I want to make sure it comes out positive. So I'm going to say it's actually the absolute value of that, which is ky naught minus y. Well, so there we go. My area that I'm looking for is a half the height times the base, or in other words, a half k y naught minus y squared. And the fact that that's all squared actually shows that it didn't matter whether I flipped these around. It was all going to come out as positive anyway. So here's our expression for spring potential energy. And note that it's a minimum at x equals x naught, or in other words, the spring potential energy is a minimum when the spring is at its relaxed length, which we already knew. Also recall that the force associated with any potential energy is always towards lower potential energy. So in this whole region, the force by the spring must be to the right, and in this whole region, the force by the spring must be to the left, but that's just telling us what we already knew, which is that the force by the spring is always back towards its relaxed length. What we've just seen is a relationship between a force and the work done by that force. Well, as is often true of relationships between two things, we can invert this relationship. And we've seen how to invert this kind of relationship before. When two things are related to each other by an integral, then we know we can get the reverse relationship using a derivative. I'm not going to go through this inversion in detail because it involves something called the fundamental theorem of calculus, which you probably haven't learned yet. So I'm just going to sort of do a hand-wavy argument. Just like I did when I was deriving the spring potential energy, we need to do a little bit of sleight of hand with our system and think of a situation where when positive work is done on the system by some force, this results in a decrease of potential energy in the environment. And when we do that, and then use this inversion of integrals turning into derivatives, we find that the x component of the force is the negative x derivative of the potential energy. We've actually seen a piece of this before. That negative sign there is telling us that the force must point from high potential to low potential, and we saw in an earlier unit that things tend to accelerate from high potential energy to low potential energy. This is part of a continuing theme that we've been seeing. Potential energies are always associated with some force, which is the force involved in the interaction that that potential energy is describing. And let's see two examples that we've already been looking at: gravity and spring forces. The gravitational force is associated with a gravitational potential energy, and spring forces are associated with spring potential energies. So in the case of gravity, if I set y to be positive up, then the gravitational potential energy is mgy. And if I take the derivative of that with respect to y, I can get the y component of the gravitational force, and it comes out as negative mg, exactly what it should be. Similarly with a spring force, if I set the x-axis along the spring, then the spring potential energy, as we've seen recently, is a half k delta x squared. If I take the derivative of that with respect to x, I'm going to get the x component of the spring force, and it comes out as negative k delta x, which is the familiar form of Hooke's law. Since this is going to be a key idea through Phys 1204, let's make sure you know how to do it. So here is a graph of potential energy versus position for some object, and we want to know what the force is, the x component of the force, when this object is moving through x equals 3.5 meters.